Okay, so hi everybody. So low energy lepton experiments means experiment with muons. Okay, so that's what we are going to talk about. So the first slide is just who am I? Just because I didn't know if I would be introduced. But as Diego said, I studied in Pisa and got a PhD at the University of Pisa on the MEG experiment. Who of you knows what MEG is? A lot. Then you will be interested in what we are going to discuss today. And I spent a lot of time at PSI. I also got the PhD in collaboration with PSI, which is the Paul Scherrer Institute in Switzerland, which hosts the MEG experiment. And I'm currently staff at the INFM Pisa. I'm working on MEG2. I have expertise in duct electronics and gas detectors mostly. In general, I mean, my field of research is in lepton flavor violation experiment. That's why I'm here, I believe. Okay, minutes talking about this. Okay, why those are interesting? I know that they were already introduced, but just to hit up a little bit ourselves. A transition like this, in which a lepton goes to another lepton plus something that can be nothing, or a pair of leptons of the same family, or a gamma, is quite interesting to study, because if you compute this kind of diagram within the standard model, since the neutrino oscillates, you can have a number, but it's a number which will never be accessible to any experimental setup, which means there is no standard model background. And if you see this kind of process, then for sure, this will come for something beyond the standard model. There are many channels that can be studied, and some of those will be touched in this discussion we will have together in these days. And particularly, as I said, we will discuss about muon processes, and we will discard the taus just because they are much higher mass. So the experimental setup to measure this is completely different. You need a collider to produce taus, while with muons, you will see the situation is much different. And so all of these channels are interesting because are all complementary, but among everybody, the muon is considered, let's say, the golden channel, usually mentioned, for a few reasons. I mean, we can have high-intensity muon beams, okay, which means that we have a large statistics available to be studied. It has a long decay time, which means you can transport muons whenever you want, okay? And also stop in the target and let them decay at rest. And if they decay at rest, then you have simple kinematics for the final states. And then you can do precise measurements in high rates. Background, because you need the high rate background, of course, is related to the fact that you need high intensity, okay? And, some processes and some possible extensions of the standard model, you see that if you look at muons, they are all, candidate portal for new physics. This is not something started now. It's 70 years that we are searching for this. We'll talk a little bit more in details afterwards. And the couplings that we can have are essentially of two types. This is very simplified, okay, in kind of effective field theory, or a dipole transition in which mu to E gamma is favored, or a four interaction particle in which mu to E conversion, or the decay of mu in 3 electrons, is favored, okay? In this model-independent approach, it's already clear that it's important to measure all the possible transition, because the presence of the one and not the other can enlighten the possible, if any, nature of the new physics beyond the standard model. But it's also true that a higher order, the both couplings are considered for all the decays. Okay, so the combined measurement of all the results then gives a lot of information about physics. In effective parametrization, in which you have this Lagrangian with two terms, one as a dipole and the other contact, ruled by this K factor, you see that as a function of this K, you see these curves that are the excluded region for the approaches of the muon physics for mu T gamma, mu T E conversion, mu T 3E. And you see that mu T gamma tends to exclude a larger portion, at least for the values that are considered in this table, that are the one that are going to be accessed by experiments, as we will see afterwards, to exclude the dipole interaction, while for the other, it's more favored the mu T conversion. Okay. And that's another plot in which we have these couplings, and we'll see that how the mu T 3 and mu T gamma experiments are complementary in making assumptions, putting limits on the values of these couplings. Okay, I'm really quick at this point because just to give you an overview of what we are talking about. But this is not the outline of the lecture, so we know why we are doing. Now we want to see how we are doing. Okay, so why and where we use mu for this kind of search, how we can look into muon decay, so how we can build a beam of muons and exploit it to study the decay, who is doing it, and in particular, the challenges in this field. So I will try to focus on experimental techniques, okay? So challenges and solutions that are adopted, and maybe also comparison with two different options and why a solution was adopted and not the other. Not today, but I mean, this list in these days, I mean, on Friday morning, I will also discuss G-2 and mu-DM experiments, like because they were also mentioned this morning, and how this can enlighten some informations or the standard model physics and beyond. But again, I will tackle this issue from the experimental point of view, how we can measure G-2 and how we can measure the mu-DM. And then finally, new ideas that came just last year or so by discussing with Diego about muon physics in MEG and how this interaction, I mean, let's start new ideas and measurement that are possible in MEG2, and maybe will be carried on, who knows, in the near future. Okay, so let's start from this picture here. This is Atlas, I guess most of you, or all of you knows this. And this is just a link to the lecture by Pagan Grisso Simone that were given at the beginning of this week, in which he discussed all the experimental, experimental physics. So how the detector works, which kind of detectors are used, and how they are built up in a very large experiment like this one. And today we are just approaching the same problem from another point of view, which is this one. I don't know if you see the difference among the two slides. Maybe I can go back and forth. Okay. This is the MEG experiment, and this is the typical size. This is more or less in scale. I kind of measured a little bit. So this is not just a picture for you, but a lot of information can come from this picture. At first, there is a completely different approach. The Atlas or LHC experiment are general purpose experiments in which we have the usual onion detectors, in which we have silicon tracker inside, maybe another tracker, around the silicon vertex. Then we have TRD detectors, PID detectors. Then electromagnetic calorimeter, then an hadronic calorimeter, and then at the end, muon chambers. With all of this, covering, if possible, the 4 pi, we can search for many channels. And one of the keywords of ATLAS is redundancy. Okay, redundancy means that you can measure the same thing in several ways. Okay? Well, redundancy is forbidden in MEG, for example, as you will see, because it's a single purpose experiment, a low energy experiment, because when we are talking about muon decay, we have a particle of 100 MeV decaying at rest, as you will see. And then the decay products at most have, at least in mu gamma, okay, half the muon mass, which means the highest energy you have in your detector is 52.8 MeV, which is pretty low. And you have many issues with those energy. Multiple scattering is a dominant limitation parameter of any tracker. It's difficult to have a good energy resolution for the photon at that energy, and so on and so forth. And for this reason, you will see we have the detector is divided in two, one part devoted to the positron and one part to the photon only. Okay. This slide you have already seen, and I'm not commenting this list, but what is shown here are 3 main facilities so far these days, in which we have muon beams available. For continuous muon beam, which means that a beam which time structure is continuous. So muons are coming and are arriving at the target of your detector continuously is PSI, which is here near Zurich, in which we have 2 experiments running, mu2 gamma and this is mu2 and other 2 facilities which are not ready in the sense that are under construction a bit, because they are exploiting a new idea of using muon beams, which are pulsed muon beam, in which they are also building in parallel with the beam facility 2 experiments to measure mu2E conversion. One is mu2E at Fermilab, and the other is COMET at J-Park. The fact that the mu2E is at Fermilab and not PSI, or vice versa, mu2E gamma is not in COMET, is not by chance. It's not because we prefer to stay at PSI, because the technology of the research imposed to use continuous muon beam for mu2E gamma, so to stay at PSI, in which we can have that beam intensity, and the other 2 to stay at new facilities like, I can also use this one, Fermilab and J-Park. Yes. Okay, so again, this picture, what are we talking about? As you can see here, we have 3 main channels that has been searched since hundreds of years, 80 years, 70 years, whatever it is, because it was 70 before, but the slide was old by a few, so then it's 80 now. And the channels that we are looking into are the mu2 gamma, which has been the first measurement at the muon decay, searching for something like an excited electron here by Pontecorvo and Higgs. And then this limit decreased with this curve, which is not linear because it tends to saturate a little bit during the years. And let me just start on this kind of historical perspective of the muon physics, started from his discovery by Neddermeyer and Anderson. And I just read again this paper in the last days. And it's very fascinating to read this kind of paper back to hundreds of years. And what they have seen is that they were looking for particles in one absorber. And written in this paper, you can find it is interpretation of penetrating once and counter very difficulties. So they've seen some particles that just came out from the detector almost with the same energy as before. And this could not be identified with the known particles at that time. Like it could not be an electron, okay? Because an electron, if you go into 1 centimeter of platinum, I mean, start to shower or so, okay? So you see something coming out, which is very different what was coming in, with a lot of energy loss in the mean, while this particle, okay, this is something new. And so nature of cosmic ray particles was kind of unknown, and this is the discovery of the muon. And then people start thinking, what kind of particle is this beast, okay? And 10 years later, Conversi, Pancini, Piccioni made this experiment in which they looked at the probability of escape of positive and negative of these mesotrons, okay? And it was supposed that this to be the strong force quanta, okay? So that's supposed to be a pi. If it is a pi, then the minus charge of this particle would be captured in the detector, okay? After their measurement, in which they don't see real difference among the two, the great yield of negative electrons from carbon show a marked difference between it and iron as absorbers. And so the calculations of the K probability, they force to doubt their estimation, so they don't see the same behavior as expected to, okay? And then going then later and later, it was thought that being a lepton, maybe it's an excited state of the electron, okay? And if it is an excited state of the electron, the mu to E gamma decay should be kind of easily possible and of the order of alpha, okay? Or something like that. So 10% or order of that order of magnitude. And this was searched by Hinks and Pontecorvo here. And at least, since they didn't observe this, it was the evidence that the two particles are not the same. Then the neutrino was discovered, and a neutrino was discovered. So if it's just one neutrino, this can be somehow taken into account in the loop, in the muon decay, and the mu to E gamma should be possible at 10 to the minus 5 level. Then, when they reached the statistics and the precision on the measurement enough to go behind 10 to the minus 5, then the two-neutrino hypothesis raised. And going on, we end up with MEG, which set the limit at 10 to the minus 13 in 2016, something like that, which is the last. Okay, this is not the last result. We have new results since a couple of weeks, but let's say that this is the last result, the best results in this search. And this is not just measuring cosmic ray, of course, because also the way that the muons that you use are an ingredient in this kind of search. With cosmic muons, you cannot do much better than this. Okay, for several reasons. The muons coming from the sky are high energy muons. The mean energy is 4 GeV at the Earth level. And it's quite difficult to stop them, okay? And so it's inconvenient to think an experiment using, muons from cosmic rays. Another idea would be to use stopped pions. So if you can somehow produce pions, and we will see how we can build muon beams soonish. If you produce pions in a target, in a thick target somehow, and you stop them, they decay mostly to muons that probably will be even stopped in that target because the momentum of the muons out from the pion decay at rest is very small. And then you can observe the decay of this muon, which is somehow in the external layer of these targets. And this is the technology exploited till the 70s. And then we start really using muon beams. And you see that all the steps in this technology is also reflected in the improvement of the limits. This is not just, of course, accelerator technology, but it's also detector technology. Okay, so again, what do we measure? Mu2 gamma, it's at body decay. So we have two monoenergetic particles as in the signal, and the two are produced, of course, at the same time with the same energy and back to back, as in this sketch. While for mu2e conversion, you have the muon captured in a target like aluminum, and out from the target you just an electron exits. So it's a quasi-two-body decay in the sense that we have also the nucleus that takes energy, but in the final state, since the nucleus stays in the target as it is, we have a single particle detected. And this is very important for the way we detect this signal with respect to the others. The third one is the mu2 It's a three-body decays, which means the kinematics is a bit more complicated because the three particles may have any energy in principle, ranging from half the muon mass to very few MeV, okay, and track a very low energy electron or positron is not an easy task. And to detect them, one has to measure all the energies and build up. I mean, the sum of these three energies should be the mass of the muons, and the three particles are in the same plane. And okay, since the muon decays at rest, the sum of the vector should be 0, which means they are in the same plane again. All of this, apart maybe for the last one, which it's hard to call exactly simple, but let's say are kinematics that can be observed, but they are pretty convenient if the muon decay at rest, okay? But being an LHC experimentalist, having a muon stopped somewhere should sound not so, you know, natural. Because usually, if you look at this detector, okay, as I said, at the end, the outermost detector usually is called muon chamber, because the muon is the last one that will stop in your detector and usually escape it, okay? Because it's a lepton, so it doesn't have strong interaction. Only electromagnetic, because the weak interaction, I mean, is not kind of usable in detectors technology. And it's heavier than electrons, so it doesn't have Bremsstrahlung, so it doesn't produce showers, at least for energy of a few tenths of GeV. For very, very high energy, of course, you have also showers from muon, but usually they don't do much Bremsstrahlung and heavy showers. So they just lose energy for ionization through the path, but initial energy is large enough to escape it. So how can we stop the muons in our detector? Okay, indeed, it is possible. Otherwise, we would never use it. But I think it's can be discussed a bit together because maybe we never thought too much about this, and it's interesting. Okay, so let's start with pi's. You know, if you have a pi minus, for example, or a pi plus, it decays in a pair of electrons or neutrino, or muon and neutrino with this weak decay, okay, through the exchange of W. If you, I mean, this is kind of standard examples in particle physics at the university. Most everybody, I guess everybody studied this. And because naively, you would say, okay, the electron has smaller mass, so it's favored. Pions will always go to two electrons, right? Indeed, it's vice versa, and the problem is due to the direction of the spin, okay? Because neutrinos are massless, so the neutrinos are always left, and what remains has to be muon of electron, and since muon is heavier than electron, it's more possible to go left also, being a muon plus instead of electron. Okay, so if you have a large number of pions, then you have also a large number of muons. Okay, and if you take the PDG table, you see that 99 times 99% of the decay of the pi plus is in muon plus. In this is another two-body decay, which means that in the center of mass of the pions, the momentum of the muon is fixed and it's not so large. It's not so large because the mass of the muon is not that different with respect to the mass of the pions. Okay, so out from a pion decaying at rest, we have a muon with momentum of 30 MeV over C, which is not, I mean, it's far from being a highly relativistic particle. Then, if you look at the beta block function, here is a standard plot taken from PDG. This is the formula. If for muons of energy of momentum of this range, we are in the left part of the curve in which the energy deposit goes, I mean, mostly like 1 over beta square. And this means that the energy loss is not negligible with respect of its own energy. And indeed, the range of the muons from pion decay in mylar is order or less of 1 millimeter. Okay? So it's quite easy to stop them. Indeed, it's more easy to stop them than let them go. Okay? While at cosmic ray colliders, we are in this region in which the delta and the X is at minimum, so they are MIP particles. So the energy loss is kind of 2 MeV per times for number of X zeros. And their energy indeed is more the GeV, then okay, they travel a lot. Okay, so this is exploited at the facilities that I described beforehand. This is the map of the Paul Scherrer Institute beam facilities. Everything starts from a Cockcroft-Walton accelerator here. It is the main injector of all the lines. After this linear accelerator, the protons are extracted in this injector cyclotron. That's increased the energy up to 74 MeV for protons, and then they are transported to the main cyclotron here, which is very powerful in the sense that out from this, we have 2.4 milliampere current of protons, which is not a negligible number, okay, for a power of 1.4 megawatt. And we extract positrons of almost 600 MeV, okay? So the protons are routed everywhere, and the PSI is kind of famous for having beams of pions, muons, and electrons that are created as a secondary products of the interaction of these protons on targets placed around, okay? We have two main targets. One is, if I'm not mistaken, one is M, which is here, and one is E, called which is here. And indeed, this area here is called, okay, it's written also here. Then, okay. This area here is called pi 5, and that's the area in which MEG is installed. MEG and Mu23 together, happily together, I would say. This energy value is not just a random numbers. Okay, question. What's the reason to have this kind of energy and not high one? If you have an idea. No. Okay, step back. PSI is famous for having lines and beams with pions, muons, and electrons. Okay, what does a proton when enters a target, which is carbon usually, produce pions? But what if the energy would be 1 GeV? Okay, we should make all the calculation, but let's say much higher than that. You would have phase space to produce something else, not only pions, autocounts, for example. So with this energy, you are below the threshold of producing counts, and you just produce a lot of pions. Okay? Then this is the proton beam going here, and here we have our target, which is this piece of carbon rotating. Yeah? No. The idea is just to produce pions, as many pions as possible, to be below the count production. Okay.
For production of pions from resonance, that's like if you just hit a specific energy, you would make a lot of this resonance gaining the pions.
That's yeah. I got your point, but I mean, I've never made the calculation if we are in a resonance or not, but I don't think so in this case. Okay, I guess just they produce pions out of resonance on carbon. Okay, because you know it's not proton against proton, but it's within carbon, because then there are also the nucleus and so on. I'm not sure. Okay, and you produce, of course, more positive pions than negative, just because conservation of charge. No, maybe in pairs. No, okay, cancel the first statement. And this is the proton target, which is rotating, okay, just to dissipate the heat, because the beam is like the point of this laser here. It's very small, but produces a lot of target, of course, impinging a lot of, heat impinging the target, and then it rotates. And so out of this, there is this channel in which we can collect, in principle, all the particles produced. But what we are interested in are the so-called surface muons, which I don't think, okay, we don't have a slide, but in order to collect the particles, you need a magnetic battle to take this flow out from the target here and drive all the muons in your beamline, okay? And for this reason, in order to be this collection efficient, the momentum of the particle that you want to collect are important. So depending on the setup of the beamline, you can select which kind of muons you are interested in. And it's even pretty important to have monoenergetic muons extracted, because one of the good point of this kind of search is to have a target as thin as possible, because effect of multiple scattering or energy loss struggling in the target, for example, are one of the source of uncertainties of this kind of a low energy experiment. So in order to have a target as thin as possible, you want to have monoenergetic muons, and to degrade their energy with some degrader, which is placed kind of here in this line, beam line, and then let them arrive with very low energy to be stopped in hundreds of microns of mylar at the center of the experiment. And the muons that are more in number, as more in number, so more larger population is so-called the surface muons, which are the muons coming out from pions that decay at rest at the surface of the target. So then they have those famous 30 or 29 MeV over C, and they can be drove to the target. Then let's try to make some very naive and easy calculation. What is the intensity which is needed for mu-T gamma search? Okay. So, of course, first question is how do we measure a branching? What is a branching ratio for a decay? Exactly. So we have to measure a branching ratio for a signal, if we are looking at muons, is the number of decay like the signal is, you count, okay, divided by the number of muons that you collected and analyzed in your experiment. Of course, then, and you will see after kind of 60 slides, how to compute this is not that trivial, but okay, at the first order of magnitude, it's just the number of muons on the target. Okay, and this is physics, whatever it is, in the sense that we have to look into, analyze the data, and okay, fight with background and so on and so forth. But this is related to your beam, okay? So this is the product of the rate of muons that come out from the main beam line and stops in your target times the DQ time. Of course, the DQ time is not a free parameter in the sense that, okay, the experiment can last few years, 10 years. But in particular for experiments like MEG, which are single purpose, dedicated, and so on, you don't want to do shifts for 20 years to search for one decay only, okay? So this has to be the order of a year. This is true DQ time. I mean, when you take data, you have stops of the machine, you have to calibrate the detector, which is not DQ time for the physics search. You have that time, you have inefficiencies. So 1 year is a good number because finally will be in real life kind of 5-ish year if you put here 1 year, okay? So if the goal of the branching ratio is 10 to the minus 14, just because that, as I showed you before, okay, we are kind of here, so you want to go below by 1 order of magnitude if you, I mean, start and build a new experiment. Okay, you want to do something that stays for a while in the books. And then the rate is of the order of 10 to the 7. Let's have a look at the facilities. Okay, we have more facilities than the one that I showed you, the planisphere. But here we have the PSI, and what you see is that the DC rate, which means continuous, is up to 2 to 4, 10 to the 8, okay? Which means, okay, we can do the experiment at PSI. If you look around here, available of this intensity, you find nothing because we have a triumph, a beam, which is available, but 2 order of magnitudes less intense. You have in Osaka, but it's 3 order of magnitude less intense. While there are projects, this is, you see the date here, an old table, and all of these goals are not reached yet, mostly. So, okay, this is still the case. And one important thing that we can note now is that, as you see, the muon beam rate can be larger than what we need. And indeed, it's larger than what we use in MEG. And this is quite important because it's not just how many muons you measure, but the resolution that you have and the precision you have to measure the signal that also counts. And here you also have two columns. Okay, I'm too slow. Here is the column for the continuous beam rate, and on the right for the pulse. And you see that you have one or you have the other. Okay, and that's why experiments are or here or there. Okay, so again, facilities experiment dedicated to the facilities that you have. If we do a step back, then we can also have a look at the backgrounds that we have. Okay, these are kind of independent of the setup that you build. They are related to the physics of these decays. Okay, indeed, with the setup that you build, the experiment that you build, then the rate of the background that enters into your signal region can be larger or smaller. Okay, but nevertheless, if you have multi-body decays like mu2 gamma and mu2 3, finally, since you are forced to have a high enough muon beam rate to reach your goal, okay, you cannot go smaller than this, you will be dominated by accidental background. And the accidental background scales like the instantaneous beam rate. And so, two beam lines that gives you 10 to the 7 muon per second, in case that beam is continuous, then the accidental background is a certain level. If it's pulsed, it means that in a short amount of time, you have more muon decay, and then you are killed by accidental background. Okay, so what counts is the average beam intensity. Is not the average, but instantaneous. And if instantaneous is identical to the average, then you keep the accidental background under control. And that's why mu2 gamma and mu2 3 are at PSI, because there the muon beam is continuous. While when we have only one particle at the end, you don't have pile up. You cannot mix, let's take mu2 gamma. The accidental background means that you take a positron from one decay, a photon from another decay. They are so close in time that mimic this just to be one decay, okay? And this enters in your background, okay? If you have just one particle in the final state, one particle is one decay. You cannot mix up anything. And then you use pulsed beam here, and we will see how, because it guarantees more performance. Okay, so let's start from the mu2 gamma case. Okay, this is not a surprise for you because that's where I work, so you know it's easy. Okay, signal and background. This is the standard slide that is always shown in a conference. The signal I already described, back to back, same time, same energy, and the background. We have a physical background, let's say, which is the relative muon decay, in which the two neutrinos doesn't carry in many energy, let's say. So the two, the photon and the positron are very close in energy to the signal region. Then they are very close to be back to back, and of course they are emitted at the same time. But if you take into account the probability of this, with the resolution, what does it mean that the photon is close to the endpoint of the spectrum? Means the detector is not capable to say this is close to the endpoint or it is to the endpoint. This means that this depends on the energy resolution of your detector. Okay, so in principle, improving the energy resolution, you can remove any relative muon decay for any given beam intensity. So there is nothing to do with beam intensity here. Okay, and so if you have good enough resolutions, you cut away all the relative muon decay, and if you see something, you are sure that it's mu to E gamma. But the problem is that this is not true for the accidental, because this is how the probability of an accidental scales, and as you see, it's proportional to the rate of mu, plus others that we are going to discuss. But given the rate of mu of 10 to the 7, 4 10 to the 7 for MEG2, for example, but also for the previous edition of this search with the MEG experiment, the accidental is the dominant. Okay. Now we want to discuss with you why the formula is like that, because at first order is not so difficult to understand. Let's go contribution by contribution. Here with delta E, delta means sigma in a sense. Okay, is the resolution of this parameter. Okay. So here is a sketch from theory, let's say, of the background close to the endpoint, which is this curve here in light gray, which is flat, and the signal, which is a small slice at the end of this flat region. And then to count how many background, so standard mu decay Michel positrons can be in the region of your signal, just integrate a flat distribution in a small region, and then it's kind of a number, okay? And here is how real life is. These are experimental data from MEG. As I said, in light gray, you see the theoretical distribution. Here, with this histogram, indeed, you see the real distribution. And you see that this drops a lot and kind of dies at 43 MeV. And this is the effect of the acceptance of the detectors. And this is quite important for MEG. It's a choice. And I just want you to note here. And at the end, we see the PDF drawn on the edge of the Michel. You'll see how the resolution is good, fairly good. But we'll discuss this later on. Then we go to E gamma. The spectrum of the E gamma indeed is not flat, but is rapidly decreasing. And you see here in red, there are many points. I don't want to discuss overall those, but the main contribution is the background coming from photons from the muons, of course, decaying in relative decay. Plus, there is also a small contribution from cosmics that enters the detector. But the point is that if you integrate these in a region like the light gray here, which is the resolution that we have in this measurement, then you see that this is with a power of 2. A better resolution means that this red slice can be larger or smaller. The smaller is this, the smaller is this number, of course, and then the background is taken under control. Being a second power, the resolution that you have in the photon energy is very important to do a good search in mu to E gamma. The same for the relative angle, okay? While for T gamma, the MEG background, which is accidental that you expect, it's flat. And then the situation is pretty similar to the one for the positron, okay? Okay, and this is real data in which you see the flat distribution of accidentals and this peak, which is unfortunately not the signal, but which peak is this? Which kind of signal is this? Not mu to E gamma, because it would be nice, of course. Any idea which kind of, where comes from this Gaussian peak? This is the time difference of positrons and photon. For the middle one, exactly, for the middle one, okay? And you see in numbers, if you want, that the area, which is pretty easy to calculate, of this Gaussian is much smaller than the area of the, of this flat top, okay? And this is taken not in the signal region, but a lower area of photon in which, given the distribution here, we have much more events than here, okay? Okay. Now we want to build this experiment, right? And I'm going through all the detectors, but my goal is not to describe you the detectors, but the idea beyond the detectors, okay? The technology that we use, the techniques. Since we have muons decaying in the center and decay products of low energy, everything has to be thin. Okay, in particular, the ideal tracker is transparent. Not tracker at all. That's the ideal, of course. And then the choice of the tracker is to have it as light as possible. Okay, the same for the photon. The photon goes into a calorimeter, but before reaching the calorimeter should arrive without losing any EV, nothing. Okay, and so the material that you used for the target, for the tracker, and for the cryostat itself, because this is a cryostat you will see afterwards. And here in the light gray, there is the magnet. I mean, everything should be very, very thin. All detector has to be fast, or at least fast in such a way that can tackle the high rate. And this is true for all the detectors, even the drift chamber, drift chamber is not famous to be a fast detector, but it's also the idea beyond any choice that you must measure your particles as fast as possible and remove them from the active area of the experiment. Otherwise, you will be, the pileup will kill you. And stable, because we take data for 3 years, we want to see a tiny effect at the edge of our, phase space, and this phase space has to be measured and stable for all the data taking. Okay, and this is important for background reduction. Okay, let's start the measurement of the positron. Okay, how can we measure the positron? No, please. Cherenkov. With the Cherenkov, you do particle ID. It's difficult to measure the energy, right? For the positron, what we need to measure is the direction emission from the target and the momentum, okay? So in order to measure the momentum, usually we use a kind of a tracker in a magnetic field, okay? But even the choice of the magnetic field is not that trivial, because you have to remember that we have 4 × 10⁷ positrons emitted at the center of the detector that are spinning into the magnetic field. And if you use a standard solenoid, there are 2 problems possibly. The first is that if a positron is emitted close to 90 degrees, it makes many turns in your detector volume, which is this one, before going out. And this kind of track is impossible to measure because they will pass probably to the same wires many times, and this will be we just let your detector to be blind to anything. And even those 5 tracks have the same momentum, but emit at a different angle. What you see is that the turning point of those tracks is different, okay, which is not typically, this is the PT, I mean, in any standard solenoid measurement, the PT is different. But if you want to tackle the intensity issue, you want to have your sensitive volume as small as possible to throw away what you don't need and have a full acceptance for what you need. As I've shown you before, we have an acceptance that is very sharp at 40-something MeV. And in order to do that, we exploited this, let's say, technology, which is this Cobra magnet, which Cobra stands for constant bending radius, in which the field is not constant, it's higher, it's larger, 1.2 Tesla at the center, and decrease with Z. And the effect of this is that first, even if a track is emitted close to 90 degrees, as soon as he encounters this field that is degrading, there is an adiabatic transfer of the PT to the PL, longitudinal momentum, and then it's swapped away at maximum and makes maximum 3 turns in the detectors. And moreover, the calculation is made good enough that if you are in acceptance, the turning point for a given momentum is almost the same. This means that if you are interested in that momentum, you can do the active volume quite small in sense of volume dedicated to your search. Here are the pros and cons. You see, here the pros is that it is standard and cons is it is custom. But of course, if you are doing an experiment, you don't care so much if it's custom or not. In fact, you discard this option and you go for the for the difficult one. Yeah. The energy is measured much better with the tracker than with the calorimeter. That's the point. That's a matter of resolution. That's a matter of fact. I mean, a tracker, I mean, it depends on the tracker. It depends how many points, but it works much better because you will see the numbers at a certain point. Indeed, you will see after the break, but okay, first we have to finish this section. Indeed, for measuring the photon, there is it has been the attempt, and maybe it will be attempted in future to convert in pairs of electrons and positrons and track them instead of using a calorimeter. So the reason is because it's much better, the performance in the measurement of the energy is much better with the tracker than with the calorimeter. Just because here it depends only on the resolution that you okay. The material budget and the single hit resolution, that's just a track with a lot of points, while for calorimeter, the statistical uncertainties finally makes the fluctuation in the light that makes the resolution worse in average, okay? For the detection, here you have the energy loss, okay, of the positrons in various material. I mean, what I want to say that given the energy from the decay, we are in this region here. And in this case, electrons are minimalizing particles. This is not true for muons, but electrons are much lighter. So we are here, and we are, let's say, far from, or below, not far, at the same level, but below, from the, when the energy loss for Bremsstrahlung, I mean, it's larger than the energy loss for ionization. Okay, so you can use trackers. You should not have too many problems with Bremsstrahlung, or you will lose some of the positrons because of annihilation in flight or Bremsstrahlung. But at least you can use a kind of tracker, which material is still not clear, to track those positrons. Okay. Okay, technology choice. We have many options. Let's put 2 in the table, okay? Gas detectors, like this one, which looks like a picture I did. So maybe it's, well, the final choice. And gas detector is made of gas, so it's light, okay? Can cover a large volume, and which means that one channel has a definite dimension and length into the volume, okay? And so the number of channels is limited, but with standard techniques, or not standard sometimes, you can get single resolution of order of 150 microns, which is not that bad, okay? So you don't have so many hits, but with the fair resolution, but the material is very light, okay? So you suffer just a little bit by multiple scattering. With a solid state, like this one, you use solid state technology. It's a compact size. in the sense that you have a channel, if a strip, which has a dimension of 100 microns, which means that the resolution is much better than 100 microns. Okay, if you have pixels, much better on both directions. And you have a high density of channels. But the problem with this kind of energy, if you take into account, as I said, okay, the multiple scattering and the energy straggling, which is the straggling in the energy loss is the distribution of the energy loss into the material, okay, which is not definite, but has a width. And this is this width that, of course, is some quadrature to the resolution that you get from your energy measurement because you have this. And this is kind of simulated in terms of thickness of silicon, okay? This is the multiple scattering energy straggling in silicon. And you see that 300 microns of silicon gives you an angular uncertainty of order, for example, 30 milliradians, and an energy straggling of close to 5% at, okay, of course, this is on this side, you should see the energy like this one, so numbers are a little bit smaller because here you see the fact that the dependency of the multiple scattering of the moment of the particle. But since the dimension of a single layer of silicon sensor is not usually much smaller than 200 microns, you end up with the fact that given the fact the helium-based gas detector that can be used to fill the drift chamber has an X0, which is order of magnitudes longer than the silicon, finally, for this kind of energy, the choice that is the winner one is to use a gas detector. This is a picture of our drift chamber open in the lab. Is a single volume. It is a very low mass gas, which is helium isobutane plus something. Otherwise, it doesn't work. But the nice thing is this something that we don't know why let it work, which is very, very nice. And one full track into this is equivalent of 200 micro silicon detectors. Okay, so you see what you gain. Of course, you pay in the fact that you have less hits, but finally, you can get the performance that you need. Just some details on how it is built. Those are the two end plates. This is 2 meters, and the wires are mounted in these PCBs here that are placed in this drum. You place the wire, and then you solder it, you extract, and this is the wires that are aligned to in the wiring machine on the pads. And of course, if you have a very light chamber, you have some challenges, okay, to tackle. So this is a draw of a drift tube that can be our drift cells, which is squared in this case, but I mean, nothing changes. And you see that the ionization is not continuous, but we have spots. In our case, the distance among the two is almost a few hundred of microns. So it's a lot, just because our gas is very light, and so the interaction are so rare that you have poor ionization into the cells, which is good because you can measure the track with a very good resolution and the angles very good. But then out from the electronics chain, you have this kind of signal. This is a waveform out from one of our anode wires, in which you see, okay, and the left and the right, this is just noise. Okay, it's just the pedestal of our electronics. And here you see some peaks, okay? Those peaks are indeed the result of the drifting of this independent cluster from the ionizing track to the wire. The point is that usually what you do with a drift chamber, you have, this is the drift volume. if you have a ionization which is continuous, you want to measure this distance here, which is B, the impact parameter. And usually the closest cluster to the real B is so close that measuring this time of drift, which is, which is this black arrow here. So what you measure is the time of arrival of this, and in an independent way, you know when the truck is passed through here. So this time reference to the time of the particles in your detectors give you this distance. Okay, if the ionization is continuous, the edge of this waveform is indeed this drift distance. Here, the problem is that you have one hit here, one here, and one there. Okay, I do exaggerate. Indeed, so if you measure the drift time, you measure this and not this one. Okay, which here is to measure this right here and not the other one, which means that your measurement is biased. You tend to measure something more than what you really measure, and this creates issues. Can be recovered if you have the full waveform, and this is one of the reasons why we have full waveforms, we will see afterwards. Then looking at the peaks, it is just, I'm just playing around, it's not the same, okay, it's not a real case, but looking at all the peaks, maybe with some, you know, refined algorithm, maybe usually neural networks and so on, from the distribution of the peaks in your event, you can have a good estimator for the impact parameter. Another challenge is that you have large drift cells, okay? So in this high rate, when you open the window and look into, you have a lot of hits, and doing the track finding is not that easy. Here, there is a real event. The good tracks is the green one, and okay, I bet you, but looking by eye is impossible to find out the good one out of this crazy hit distribution, okay? And this won't be the case with the silicon detectors because you have very miniaturized detectors in which you can, I mean, the pile-up within the same strip is very rare. They are, I mean, if you can look like with a microscope, they are more, I'm not saying it's easy, but the pile-up is very, very less probable. And then, I mean, it's even more, it's easier to do the track finding and so on. About the performances, with all of these tricks that I said, we have a resolution of less than 100 keV in momentum, which is a fairly good result. This is not all, but almost. We need a time, as I said, and the time is essential for mu-T gamma because one of the variables we study is the TE gamma, and drift chamber being a slow detectors with the drift time and so on and so forth is not good to measure times. Indeed, drift chambers need a time reference for the track, okay? To reconstruct these impact parameters, you need a reference time because essentially, okay, let's have a square cell. A track that goes here or goes there have two different impact parameters, which are reflected in two different times, but with respect to the reference one. The two times are, if you don't refer to anything, are just two times, and you don't know which is closer or farther to the real passage of the particle. So you need the reference time. And what we use is this matrix of scintillator tiles read out by silicon photomultipliers, if you know them. Otherwise, you can ask me in the break. And a positron runs through these tiles and goes through them in average, goes through 8 of them for a signal positron. And we also exploit the fact that when you have multiple hits of the same particle, your resolution improves with the square root of n, where n is the number of heat tiles. Indeed, starting with a single tile resolution of 100 picoseconds, you end up with a measurement of 40 picoseconds for the final measurement. Okay, that's all for the positron measurement. Maybe we can stop 5 minutes if you want, or I can go if you prefer. It's up to you to tackle the photon issue. Let's stop. So again, let's start from an historical perspectives. And as I said, as you've seen, it's not the first Dimitri gamma experiment. And let's see other choice just to learn something about that. Late 80s was an experiment called the crystal box, in which there is no magnetic field, the stopping target at the center as usual. Then there is a drift chamber at the center. Okay, but we don't care. We're talking about photons now with no converter, so photons just go through. And the measurement of the form momentum of the photon through these crystals of sodium iodide. If you ever heard about this, this design, which is sketched here, gives a large acceptance. A good energy resolution because the light yield, okay, is not only light yield as we discussed afterwards, but at least light yield is one of the components because it gives you the statistics you can collect in terms of photoelectrons. Okay, the light yield is fairly good because we have to remember that the photon we are measuring is low energy. Okay, so the statistics is good enough. The decay time of the sodium iodide is not that good. It's 250 nanoseconds. You know, so you see, you expect to have a fair timing. Okay, not picosecond level as seen before. Okay, so the solution can be okay. We use a calorimeter. This is a highly segmented crystal sodium iodide, and this just to let you know the measurement they did. Okay. Another solution that I'm coming to you that you asked beforehand, the calorimeter for the positron, which is of course possible. I mean, it's also done at LHC, okay, together with tracking, of course. It depends on the energy, you know. If you don't have the sagitta to be measured, then you cannot use tracking. But we are not in that regime here, largely not in that regime. In mega experiment at Los Alamos, they said, okay, this is wrong, but I will change. This is a small acceptance, not a large one. But they say the E gamma resolution is important, is the most important in the background probability, okay, as shown before. We want to measure this at best. And how to do that? We put on the external shelf of a detector, internally magnetic field and tracker for positron. In the external one, converter, okay? We create E plus, E minus pair, and we track them. And then we have the direction, we have the sum of the energy, so the energy of the photon, and so on. And after the recurl, here we have some scintillators for timing, okay? So the timing is kind of indirect because it's after recurl. But in principle, the resolution is good. They had some, I hope no one is from the mega collaboration here. Okay, it's also written in their paper, so it's not that I'm saying nothing bad. They had some troubles with pileup, okay, in the detector. So that didn't behave at expectation. Indeed, the limit, if you look, is not after 13 years, just a factor 5, if you want, below it. So let's say that this comes first, has some troubles. Then we had this one. And at that time, it was the best technology for this kind of search. So the next generation look in the past and tries to improve. And here comes MEG. The choice of MEG, as you know, because we have seen, is to have a calorimeter. And which kind of mean we want to use? Here are possible solutions. And you see 3 parameters that are pretty important. The density, which tells you how large you have to build your detector and how much you have to pay, of course, because the larger the detector, the more you have to pay. The light yield, which tells you about this term in the resolution of the calorimeter, the statistics one. And the decay time that tells you the time resolution you can get out of this. And here you see that, for example, sodium iodide and BGO, which, well, BGO is pretty dense. We can have a very compact one, but not so bright. And sodium iodide is brighter, but the decay times for both is not so good. So they are not good solutions. And of course, another point, in order to get finance to build a new experiment, usually you need an idea, something new, also some new technology you want to develop and that can be used abroad, your experiment. And in our case, it's liquid xenon, okay? So our choice is to use the xenon gas to liquefy it at minus 100 degrees and use it as a scintillator, okay? Is still this 900-liter volume, the largest scintillator using xenon, is not the larger xenon detectors because xenon 1 ton and so on, that line are larger than ours, but they use xenon as for ionization purposes, not only light, but also charge, okay? It's homogeneous, which means that it has to be fast because if one photon impinges the detector in one point, the light spread almost everywhere, and of course degrades the performance for the new incoming photon that will come quite soonish because we are working high rate. Indeed, xenon is fast. It has 3 different decay times. So we will see somehow why those are different, but it's order of nanoseconds, not so far from organic scintillators. And it's very bright because it has 40 photons per keV. This is a picture from inside. I'm sitting on the back face like this one of the detector. The shape is like a C that is around the magnet, and in the inner face you see this fully equipped with sensor squared one, which are silicon photomultipliers, while on the other faces we have these round photomultipliers. And the use of these silicon photomultipliers here in the interface is very important for imaging that we can do with the calorimeter for pile-up rejections and other things, but mostly. So this is the list of the characteristics of the xenon. About the density is high enough to have a reasonable size cryostat. And one challenge is the scintillation emission wavelength. It's under 80 nanometers, so it's close to ultraviolet. It's not so easy for photomultipliers or silicon photomultipliers to have good quantum efficiencies at this wavelength, just because usually you exploit photoelectric effect, and it's not. You have to find a good, material for the interface to use this. And they also have to work at minus 100 degrees, so the sensors has to be carefully tested before using it. And now I want just to draw some attention to the decay time. We have 3 numbers, and okay, apart from the first, which is the prompt one, but is not that abundant, so it's not the main contributor to the light. The other 2 are much more abundant, and they come from 2 different scintillation mechanisms. The one is the faster component after an excitation of the xenon. So you have a xenon atom alone, okay? A particle goes nearby, deposits some energy, and then it's excited, okay? And he encounters another xenon and forms a chimer, is called. Xenon 2 excited, that immediately decay into xenon, living alone happily, plus a photon, scintillation photon, okay? While the other one is slower because goes through ionization. So what happens is that first you ionize, you form, you construct this excimer ionized, then you have to search for an electron somewhere, then you form this excited state that first release some heat, and finally, only finally, which means 20 nanoseconds later, creates this excited excimer and then the light, which is the same wavelength. So it's not different light, it's the same light, but it's just a little bit later. And this is something that can be also used in the experiment. That's why I'm talking to you. If you have two different particles and minimum ionizing particle, like a photon that makes kind of a shower, so it's 53 MeV is not really a shower as you might think. It goes through 2 or 3 steps and then it's absorbed, but it's a very small shower. It goes primarily to ionization chain and has this waveform that has this tau on the right tail of the order of 40 nanoseconds, while highly ionizing particle, like an alpha particle, okay, goes through the excitation state and gives you a quite narrower waveform signal. Okay, here is just a waveform, but okay, indeed, it's light that has this shape. Since we use alpha particle inside the detector to calibrate the quantum efficiency of the photomultipliers and of the silicon photomultipliers, the fact that the two has this different shape can be used in the reconstruction phase to select only alpha events among all the events that you can have. And it's pretty convenient. And it's also exploited at trigger level. Okay, I'm not talking into these details, but just want to tell you. Okay, so detector works. This is the results that we can have. You see, we have a fairly good resolution in energy over 2%. And we have resolution which is a little bit better for events that doesn't convert exactly after entering the xenon, because in that case, the light is absorbed by just few sensors and you have some saturation effect, but deep events have a better performance. This is the timing that you can get, and since the xenon is quite bright, we have 80 picoseconds resolution even in xenon. Okay, you have to compare with few nanoseconds that they had in the past, so it's a huge step forward. And this is the result of some events in which we put this mask in front of the xenon, and we can reconstruct this mask out of the data. With this pattern, you can measure the position of the conversion of the photon decalorimeter resolution, which is fairly good, of the order of millimeters, which is indeed the dimension of the sensor that we have put for like the silicon photon multiplier. The xenon is not the easiest calorimeter to be used because suffers given the temperature of the sensors and given the nature of the scintillation light from few possible instabilities that has to be monitored often daily basis and corrected for the stable operation of the detector throughout years. And indeed, we are prepared not only for xenon, this is for all the detectors, but mostly for xenon, this redundant calibration system. We have a dedicated accelerator, a Cockcroft-Walton one, which is it's not the same, but it's a little brother of the first injector of the PSI beam facility, in which we can shoot up to 1 MeV protons on lithium to produce 17.6 photons of delta photons, always have the same energy, to be measured by the calorimeter, to monitor the energy scale and the resolution, 3 times per week. Okay? We remove our target, we put another target, and we shoot these photons 3 times per week. Then, as I said, we have these alpha particles here placed on wires. And you see this is a nice run taken during the filling up of the detector. And since the alpha particles are used because they travel for a few tens of microns in the xenon, and so you know exactly where the light is emitted, and given this information, you can reconstruct, and also the amount of light, because you know the energy of the alpha particle. You can reconstruct the event and then calibrate your sensors because you know what you are measuring. But since they travel a little bit in xenon, they suffer from the shadow of the wire, which this is the wire, this is the alpha particle on the wire. They decay just after they are released from the source, and then they form these nice rings. And this tells you where the level is, while these are in gas xenon, and in gas they can travel a lot, and they have point-like, they are kind of point-like sources. And another notable example is the charge exchange that indeed is what is happening now at PSI. We are performing this calibration in which we change our beamline. We don't use muon plus anymore, but we revert to pi minus because PSI can give you pions, muons, and electrons, okay? And we put at the center of the detector a liquid hydrogen target in which we have a lot of protons, okay? To have this reaction pi minus on proton to go to pi 0 neutron, and then the pi 0 decays into gamma, okay? The pi 0 is traveling, there is a boost. So in the detector laboratory frame, you have a flat distribution of photons from 55 to 83 photons. But if you use a back-to-back auxiliary calorimeter to study a region in the xenon in coincidence with a region on the other side with this auxiliary BGO, which is a BGO, you define the opening angle of the 2 photons to be in this region here. And so you select 54.9 and 82.9 in these 2 spots here, taken a few days ago from our experiment. So it's not from books. This is what is happening at PSI. And you can measure the resolution of the xenon exactly, because it's 54.9 to be compared with 52.8, which is the energy region. So exactly at the energy region, and extract the PDF. Another notable example is the energy scale calibration. As I told you, we have some effect for which this is not exactly flat during the time, but given all the calibration system that we have, we can flatten it out and then finally have an uncertainty of less than 0.5% to be used as a systematic contribution to the uncertainty of the experiment. This slide is to show you the importance of calibration, okay? This is the 17.6 MeV line out from the xenon, from the Cocker-Fulton accelerator processes, induced processes. And okay, you take data, analyze with the calibrations that you have, and you look at the line, and this is what you get. You see this line, this other bump is a second line on the left, everything is fine, and you measure resolution. You say, okay, let's try to have a deeper look, and you search for the position of this peak as a function of, for example, let me draw, otherwise it's impossible to understand. This is the calorimeter. Okay? This is kind of this coordinate here, R phi, okay? The position on the interface. And you see that this line is not seen at the same value all over the interface. This is a non-uniformity, okay? This means that when you plot everything together, you take this, you project on the right or on the left as you prefer, and this, of course, makes your distribution larger. Then, if you use the proper calibration for the quantum efficiency and the gain of the photomultipliers, the PDE, the gain, the crosstalk, and after pulse for the silicon photomultipliers, and you correct sensor by sensor the charge measured by those values, what you have afterwards is this distribution here, which is almost flat. Here there is a small deviation for being flat, but okay, it's fairly good for us. And you see that the same plot with all the points projected, it's more definite. And you have a pretty better resolution. And this is, if you want, the C. This is the effect of the C in this formula, which is, in fact, associated to calibration, okay? If you have bad calibration, you can shrink this distribution as much as you want, but this snake-like curve will stay, okay? Okay, TDAC, just because I work on it. We have the custom electronics. The point is that we are working, again, at high intensity, and in our sensor, we often have pile-up, okay? Since we have pile-up, we want to, as much as possible, disentangle it. We don't want just a number out from each sensor, which can be a charge or a time, so 2 numbers, okay? Or 1 or 2, whatever it is. We ask to have the full waveform in a definite, of course, time span, because with the full waveform, we have an DAQ, which is equivalent of having 8,000, maybe 9,000 oscilloscope, and we can perform pretty refined reconstruction algorithm. Of course, it's not all for free, apart from the fact that you have to build your own DAQ, which is really an hard job. As you will see, you have a huge size event as something to take to consider. Then there is a trigger, which is fully integrated. It's based on FPGAs, like this one. All the boards in this system have FPGAs. And for latency issues, for the use of this chip, which is the waveform digitizer, the trigger should decide if an event is interesting or not in only, not 450 picoseconds, which is very difficult. It's 450 nanoseconds, which is also difficult, but not that difficult. And the full DAQ is read through Ethernet with a maximum rate of 50 Hertz, and this makes Diego very, very sad, right? We will see why on Friday. Okay, what does it mean to have the full waveforms? Is this one. Your event is a collection of pulses like this one, okay? 8,000 of this one, and you have to, one by one, analyze them, like having an oscilloscope. Okay, this is a nice picture of one of these crates. What about the event size? As I said, one channel is 1024 numbers of 1.5 bytes. And MEG2 has kind of 500 of these DAQ boards. Each one has 16 input channels plus 2 clocks. I have no time to tell you why the clocks are there, but it's just to have the best ever timing possible with this scheme. And so the total number of events is now 9,000 channels, okay? And if you sum up all together, the event size finally is kind of 14 megabytes, and this is only for the waveforms. One event is not only the waveforms, there is some auxiliary information that are not that large, but this is just for waveforms, okay? If you take into account 24/7, the DAQ time for 6 months per year, and maybe for these 6 months is the one DAQ full year that I was mentioning at the beginning, okay, is never really 12 months, okay? 1 year is kind of integrated. 6 months for a few years, it's per year 3.2 petabyte. It's too much. It's just too much. So we need data reduction. So in this kind of applications, what we do we have a data reduction scheme with a flexible logic. First cut is the region, so-called the region of interest. So we cut only the part of the waveform that we need, depending on the detector we are reading out, because each detector is different from the other one. If the detector is highly segmented, like the timing counter, so the matrix of scintillation types, there you have a hit, you don't have it. If you don't have it, you don't want to register nothing, and you just cut out. For a homogeneous calorimeter like this one, it's difficult to say I have a deposit or not, because sometimes it's very small, but if you discard all of this small contribution, you lose resolution, okay? So you have to write everything, but what you do a rebinning on the left tail, right, where you don't have, it's far from the trigger. So if you have a pileup here, anyway, it's far from the trigger. And the rebin size factor, it depends on the height of the signal. If you are in the core or the shower, like this red point here, you have a very large pulse and the rebin is not that much because you want all the details on the tail. While for the outer part of the shower, you rebin like this. And if you are in the violet region, you rebin the full waveform, okay? If you integrate, the charge will stay, but you lose the timing information, which anyway are not needed, okay? And with all those tricks, the final event size is 4 megabytes. Importance of having waveforms. Here is a real example of a pileup in a waveform. You see, this is okay, I don't know, but probably this is a photomultiplier, okay? Just looking at the shape of the signals. This is related to the trigger because it's the one much on the left, which is the smaller contribution, definitely. Then you have a second peak and a third peak, okay? If you have just a QDC, what a QDC does, it opens a windows, this window here, that can be selected by experimentalist in time, in width, given the needs. It has to take all the signal and so on, the length and blah, blah, blah. But if you have a standard signal, okay, you compute this charge. If you have a pileup, it just gives a larger number. Okay, that's it. It's very hard, which is just with this number, disentangle this. Okay, I have no experience, but probably what you do, you see that a part of the detector has some strange correlation that are not compatible with a single photon, and you throw away that event because it can be dangerous, can mimic a signal, okay? If you have the full waveform, you can disentangle it. And even more important, you can have an algorithm that is not available at the very beginning, but you just deploy even 5 years after you have taken the data to improve your performances, okay? Because, of course, data are there, and you can start your analysis from the waveforms anytime you want. So if you improve the waveform reconstruction, you can improve the performance of your experiment even a year later. Another example is for drift chamber. Those are two signals from the same wire on the two ends of the drift chamber. You see that here we have 3 different clusters of hits in the wire, which is not so easy to find it. And if you want to use a TDC, which is commonly used in drift chamber, it's difficult to find a way to have a threshold which is sensitive to these peaks here, because they are very, very, very close to the noise, okay? But having waveforms, you can deploy a noise reduction that can be coherent or reduction, machine learning-based reduction, whatever you can think and study, and really takes out hits in very difficult case like this one. Last but not least, for the detector is the trigger logic. MEG is, I mean, it was, I would say, a single purpose experiment. It was. And we are searching for this mu 2 gamma beast in a high background, and given the AQ that we have, we cannot, here the rate is not written. Maybe it would be better to add. We cannot go much faster than 10 Hertz, even with the reduced size event, because otherwise the dimension is out of control. This means that out of 10 to the 7 events at the source, we can, per second, we have to trigger in 10 events per second, which means a cut of 6 orders of magnitudes of the background, which is not a trivial task, and is accomplished by cutting on these 3 variables. The E gamma threshold, which is the most powerful for the reason of the spectrum being decreasing a lot. The T gamma window being of the order of 20 nanoseconds or so. And also we correlate the heat position of the photon in the interface and the heat position of the positron in this yellow detector, which is the timing counter, to have an idea of the back-to-backness of the events. We don't use a drift chamber. We don't use a drift chamber for 2 reasons. First, it's a gaseous detector, so the formation time of the event is slow, and the heat can arrive to the wire 100 nanoseconds after the track, and our latency is 450 nanoseconds, so you understand that you cannot wait for it. Secondly, it's very difficult to trigger on tracks, so let's avoid this possible. This is an example how we construct charge online, trigger level, by FPGAs, and these 2 are the 2 lines from charge exchange that I was showing you beforehand. How to perform a calorimetric trigger? We take all the waveforms and we digitize them, not with the DRS chip, not at 1.4 gigasample per second, okay, but with a slower ADC, commercial one, at kind of 80 megahertz. And we take channel by channel, we remove the pedestal that is arbitrary value channel by channel, we calibrate for the PDE, quantum efficiency gain, pulse shape, blah, 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 and we sum up all together. And finally, we end up with this waveform, which baseline is centered at 0, which is 0 MeV, whatever it is. And then it has this pulse here, and we cut on the height of this pulse, and our energy estimator is just a peak. Okay, with this, we build a very long list of triggers, because we have to supply the detector with a lot of possible data acquisition scheme for the calibrations mostly. The first trigger is MEC, is the one for physics, and then we have a lot of released trigger, like for coincidences, in which release the energy, the angle, the time, you don't care about the direction, and so on. Then you have a list of triggers only for xenon, a list of trigger only for timing counter, then you have for drift chamber and for auxiliary devices. And here, an example how we compute the efficiency, which was also described yesterday or 2 days ago, I don't know exactly when. The turn-on function of the trigger is a real example. In black and blue, you see 2 E gamma curves as seen offline with the cut on the trigger and 2 different values. Here, the trigger cut for the black is kind of out of the box here. So you see the full spectrum rising. And while for the blue one, we apply a cut, which is kind of 42 MeV or so. You see that the spectrum is nearly 0 below, and then starts and then meets the other one here. And by the ratio of the 2, you have the turn-on function in which you measure the threshold, the resolution of the threshold, and the efficiency, which is here order of 96% in this case. And if we put our TDAC in the field, you see that we are a peculiar case, but we can stay here with all the other experiments, you know? In this plot, we have the event size versus the level 1 rate. So the first level rate, we just have 1 level, okay? So this is our trigger rate. In our case, it's level 1. And here there are the curves that are the kind of isochrones in the sense of which the to compensate to have to be at the edge in terms of rate compared to event size. And we are kind of here. What I want to say that our event size is very large. It's even larger than Atlas and CMS, like in event one. And that's why we cannot go that fast in the accurate, because we are kind of limited by this. Okay. Okay, I just, not so many slides, so we can end up with Meg. I will continue for 10-ish minutes, 20, 30. Let's start with normalization. Okay, normalization means, let's start from the very beginning. The branching ratio you measure is the number of signal divided n mu. Okay? Okay, normalization is this n mu. Okay? In principle, one thing that you could do, you could have a scalar on the target, count how many muons are there in your acquisition time. Then you have to take into account the acceptance of your detector, the dead time of your TDAC, I can read it, even there, the efficiency in reconstruction, these and the other variables, the efficiency of the trigger, and many, many other parameters which are not under your control, okay? Like, for example, the efficiency of the tracker. Why I'm just saying the tracker? Because the tracker can vary at the second order his performance in terms of efficiency. For example, if the temperature in the hut, which is where we have the experiment, changes a little bit, the pressure changes a little bit, because the gain out of your drift cells change a little bit, and then the pulse site that you have, which is close to the noise, might change. So following these efficiencies is very, very, very difficult. So usually what we do is not something, striking. We use a well-known signal to be normalized on. In this case, is the standard decay of the muon, which is this one, which is Michel decay. Okay, this is well known. So what we do, we use one of these, minimum bias trigger that I mentioned before, which is this trigger 21, which is a trigger only on the timing counter. So if you have a hit at the end of the track of the spectrometer, you trigger it. Okay. Of course, just to give you an idea, the rate of this trigger is kind of 4 megahertz. You cannot recall 4 megahertz. No way. Okay. Indeed, this is taken together with the physics data, and so you don't want to disturb physics data. What you do, you prescale it. Okay, this is also a common feature of trigger system. So you just record one every other 1 billion. Okay, this means that you record 2,000 events. You have 1,995 physics data and 5 of these, normalization triggers. Okay. But this number is well known. There is no uncertainty. Okay, it's just a number that decrease the rate of your trigger artificially. Then you count the positrons that you can reconstruct in phase with the trigger in a certain region of energy. You correct the efficiency of your normalization signal with the physics signal. Then you don't have a photon here, but you put inside with this efficiency that you measure with dedicated data acquisition. Then you have the trigger efficiency, the selection efficiency, and this tells you finally how many muons you have. Now I can show you why it's important to use something like that and not to use efficiency out of mind. This is from the first run, and you see that we used different beam intensities. As I said, this is our main one so far, but this can also, in a sense, answer to your question before. Also, the beam intensity is something that you have to study and optimize for, okay? Because not only the background changes, as we have seen at the beginning, but also the performance of your detector changes. So what you expect is that every time you increase, this is the integrated normalization as a function of runtime, okay? So these are, okay, the moment in which we change the beam intensity. And what you expected every time you increase the beam is very low, then this, you change the derivative to higher values, okay? Of course, because you have more muons and your normalization must be quicker to rise, okay? Indeed, you see that there is not so much different from 3 to 4, maybe not at all, not so easy to see. And at 5, it decreases. It decreases instead of going up. Why? Because these numbers here are affected by the beam rate. In particular, the issues that we had in 2021, which are the data that we already analyzed and published, which are fine, but it was the first year of data taking. We had some issue with the DAC that could not run that fast. Now it's fixed, but it was the first year using the DAC, so we just end up in fixing here and there troubles. And also, what is still true, but not with this impact, the drift chamber, which efficiency is at the design level of the order of 70% in tracking, these decrease a little bit with the beam intensity. Why? It decreased because the pileup is a concern for the tracking. And the more muons decay, the more the pileup is. And then what you see that finally, it decreases more than what you gain by increasing the beam, even if the most effect is the DAC, as I said before. Okay. So data analysis. Now we want to measure NS. Okay. The scheme that we use is quite common. It's a blind analysis, likelihood analysis in a blinding box. So we hide this blue-white region to everybody until the reconstruction is not fixed. We use these 5 variables plus others, honestly, but okay, these are the most important. We compute the so-called probability density functions, PDFs, outside from the box. And here there are a few of the regions that are very important. This one is so-called E-gamma sideband, in which you can see events in time coincidence with low energy. And there is a small spot which should be brighter here, which is the relative decay that we have seen before. It was from here. And then the T-gamma sideband, in which you have the full background, photon background. This plane I forgot to mention is T-gamma in the X and E-gamma in the Y. And so in this T-gamma sideband, you have the full spectrum of the photon. Okay, the PDF then are extracted out from the box. As I said, in T-gamma sideband, we can extract the background spectrum for the photon with various contribution. By looking, you see, these zeros are because are inside the blinding box. We can have the distribution of the accidentals in the T-gamma 1. This is the Michel spectrum, and so on and so forth. And when you are ready, you can open that box and make a fit. This fit is in these 5 variables, and you get out how many events you measure, and we measure -2. No, -2, sorry, less than 2. -2, no. Less than 2, which, I mean, turns in a branching fraction of this order of magnitude with that data. Here you have the toy Monte Carlo distribution. I don't know if the toy Monte Carlo were mentioned last lecture. But I think that most of you know what the toy Monte Carlo is, at least who works at LHC. And then here, to answer again to your question, is a look at the events. We have 2 planes, E positron, E gamma, and here the points are the ones that were inside the blinding box. And here is relative angle, relative time. So this region here, the small here, and the small there are the regions in which you want to cluster your multi-gamma events. And unfortunately, they are empty. We have one point here, which is not so bad. But if you look in the other variable, it's quite far from the 1 sigma, 2 sigma, 3 sigma distribution of the signal. Okay? So wrap up. Yes. No, it's the contribution of cosmics. Two contributions, cosmics and pile-up, that are not unfolded. Of course, there is nothing there from muons, nothing, but there is a tail of the resolution, cosmics, that, you know, here, I mean, the PDF is 0 in this region here. So you can have whatever you want here. It doesn't change your analysis. Or cosmic rays, that are muons, they're not photons, or pile up from background. Okay, so if you wrap up, you have seen this, just some perspective. We started to work this experiment at the end of Meg and 2012. We start physics and we will take data for a few years. This is the goal. Sensitivity, a couple of papers that were published. So since next case is for the next lecture, we can stop here, I think. If you have questions, or here or from there, as you prefer. I have not to run away, so we have time. As you wish.